All right. Welcome to the first in what will be a series of uh, webinars on AI in travel forecasting, which we're putting on as part of a project for TMIP. Um, and this is kind of the introductory webinar, and we're going to give you a little bit of an overview of the project, and an introduction and an overview to AI and machine learning, what it is, and some thoughts on how it applies to travel forecasting and modeling. So, with that, um, I want to, I'll go ahead here, uh, and hopefully, oh, we got something. Oh goodness, I'm having trouble advancing the slides for some reason. Uh, all right, well, we can do it that way. All right, just real quick, I want to acknowledge that, this is, a team of webinar, but the views expressed in the webinar do not represent the opinions of Federal Highway, don't constitute an endorsement, recommendation, or specification by Federal Highway. The content is based solely on the work of the presenters, and that reflects our opinions as presenters, and that's going to be the case for all of these webinars. So let me give you start with a little overview of the project. Um, the project's called Advancing Travel Forecasting Practices and Effective Use of Travel Forecasts in Long-Range Transportation Planning through the Application of Artificial Intelligence and Big Data. And there's several parts to the project. The project began, kind of the first stage was with most of the literature review, but also kind of a scan of the practice and what's been done out there. And then there's a little bit of a deep dive, testing some new methods, and implementing them in a pilot project, and writing a case study on that. And now here at the end, we're wrapping up with a playbook uh, on incorporating AI in travel models. And connected to that is this webinar series to promote the playbook and some of the methods there. So the project focus is really more on the AI side of the title. Also is big data. The two are connected because it's part of the power of AI is its ability to leverage big data. But TMIP has produced some other materials on big data, or over the past decade, and so the focus of this is more on AI. The focus is intended to be more on practical improvements in the near to midterm. So, and if we think long term, it's entirely possible that we could think about entirely new frameworks for travel forecasting, but we're not going that far outside of the box. Rather, we're focused on kind of the near to midterm, with the thought of potentially improving, enhancing, or replacing individual model components in our model systems. And because of that, there's a particular focus on what are called AI-DCM models, which we'll explain a little bit. But they're basically a combination of logit models and neural networks, or an extension of logit models, if you will. And so, obviously, since we use logit models already extensively in our models, the idea is that to go from a standard logit model to an AI-DCM model is an incremental change, a change that can, something that can be done either in a trip-based system or an activity-based system, either way, and something that might be viable in the near to midterm. We chose specifically to focus on destination choice because it's the largest source of error in our travel forecasting process, because it's extremely hard, large problem. But because of this, it's also the greatest opportunity for improvement in our models. And we're inspired a little bit. This chart on the right is showing, comparing a gravity model to a destination choice model to a neural network, specifically one called deep gravity. This is, coming from a publication just a few years ago. And you can see that destination choice, the logic destination choice model does twice as well as good old gravity. The neural network was able to do about twice as well as that. So that's part of the inspiration for the focus of our deep dive in the project. Um, we did looking at the literature review, the first part was looking at these AIDCM models, artificial intelligence discrete choice models that combine neural networks and logit models. And the idea, the hope is that this kind of model can kind of capture the best of both worlds and give us the theoretical basis and the behavioral interpretability of traditional models while harnessing the explanatory powering and predictive power accuracy of AI. There's a number of different ways that you can combine neural networks and logit models, different model architectures that have been proposed. We, reviewed some of those, and our deep dive focused mostly on an architecture called TB-ResNets. We'll talk more about these things in some of the upcoming webinars. Um, then, we also looked specifically at the use of neural networks for destination choice. And we identified over 350 papers going all the way back to 1993, believe it or not. It was the first time somebody proposed to use a neural network for destination choice. And we identified 8 distinct branches of literature, kind of based on their citations and what they seem to be aware of. But there's also some significant differences in these different kind of bodies of literature in terms of their methodological focus and their use cases and so forth. Um, and for those who are interested in the details of all of this, it's one of the first report from the project is focused on this. As part of this, because there's so many papers and so forth, we did a model-based meta-analysis of 107 different models based on 112 data sets that were published in 81 papers. The model that we used a binary logit latent fitness model, and we're able to, the model performed well. We achieved a R squared of, over 0.8. You can see kind of that it explains the published goodness of fit values in literature well. And what we found at a high level was maybe not surprising, but generative AI was the highest performing kind of method group of things, and specifically generative adversarial networks. Although large language models also were impressive, generative adversarial networks, which are what is used for computer vision and image generation and so forth, actually performed best. Again, we're going to talk more about these things in some of the following webinars, but just kind of giving you an overview today. From that, having identified TB-ResNets and generative adversarial networks, our deep dive, in testing and implementation, we chose to use Reno as our test bed with the wonderful support and cooperation of the Regional Transportation Commission of Washoe County there, the MPO. And they had both some really nice survey data as well as big data that we were able to use. And again, this the third webinar is going to, basically go through this in detail. So this is a little teaser for that. And then, of course, this is culminating in the playbook, which will be coming out later this year from Federal Highway. which, hopes to kind of encapsulate some of this, beginning with sort of, the promise and potential of AI, some early success stories, and particularly the Reno case study. The webinar series, the first three here are scheduled. Obviously, this is the first one with Rama and I. Next week, we will have a second one that's focused more on things that are already in use, machine learning methods that are already in use in adopted travel models out there. And that's going to be, our presenters are going to be Dr. Hadi Sadr and C. Shi. And then the third one, as I said, is going to come back a little bit more to focus on some of the work in this project. We're going to look at that Reno case study. But there's going to be a number of more webinars. We're probably going to slow down the pace after these first three, maybe just have a couple of months, for the next 2 or 3 months after. But we're going to talk about a bunch of other things, including AI and population synthesis, LLMs, agentic AI, and so forth. Hope that you can join us for many of these. I think it's going to be a great series. So just a little bit of an introduction, kind of again on beginning to introduce and give an overview of AI here. Rama's going to extend this, but I'll open it up. Obviously, you don't have to go too far to read about AI. Just in the news or whatnot. This is something that has captured the attention of society. This is something significant, something very really transformative is going on, right? And it's not all good news. It's not all bad news, right? There are some remarkable achievements on the one hand, and there are some, significant problems too. And so, we try to, hopefully we can all, you know, keep a balanced perspective here. We want to harness the positive things here and use the potential of AI to advance our field, our profession and discipline. But we want to be careful and mindful too of how using AI in a way that is not thoughtful, can be dangerous, can actually create bigger problems, right? So I want to, I'm introducing things, setting things up a little bit in terms of what I consider 5 key insights of modern data science. And using just, fun, informal language, I characterize them this way. And I'm going to step through each of these. But first, I think the first thing is we don't already know everything. The second is that reality can be really complicated. And third, sometimes bigger is better, but you have to move on, and sometimes 2 models are better than 1. So what do I mean by this? First, we don't already know everything, right? One way that you can think about the shift in mindset or culture or however you want to think of it, from classical statistics, which you're probably more familiar with, but you probably had some coursework in school, to modern data science, AI, machine learning, and so forth, is a shift from a theory-based perspective to a data-driven perspective. There are, ways that people characterize this, including, people sometimes say, are you trying to, is the goal to understand or prove something or to predict, right? And, I think these are all helpful ways to think about this. I think it's helpful to think about thinking about the starting point, right? Are we starting from a hypothesis that we want to test, or are we starting with some data that we want to explore and fit some math to, um, uh, particularly for prediction. Um, uh, and so, modern data science is more practically focused on prediction. It's less focused on theory, understanding things, proving things, and so forth. And good and bad things for both of these perspectives. I think it's probably obvious, but traditional statistics, classical statistics, comes from the setting of laboratory science, um, uh, and in that context, a lot of it makes sense, right? And in a laboratory setting, you can control a lot of things, and because of that, you can limit the errors in your data to certain kind of limited kinds of things like measurement error, of particular kinds. And given that, you can make reasonable assumptions about those errors, and also the various factors at play, things that might affect something, right? But in the real world, as it were, and when we're looking at human behavior out in the wild, it's rather different, right? And uh, you know, we all, I'm sure, the whole saying, when you assume, do something with you. And uh, you know, there is a real danger that classical statistics does acknowledge of omitted variable bias and other kinds of specification errors. And a big part of what machine learning tries to do is it tries to, in some sense, take a humbler position, and not make these kinds of assumptions. And tries to learn, doesn't start from a theory that it's going to test, a model specification to begin with, but rather tries to learn the model specification, including, the structure of the model itself, and the errors and so forth, from the data. So we're not just kind of giving a formula and saying find the coefficient values, right? But we're saying, help me come up with the formula, right? And so, we can, people talk about linearity and nonlinearity. People talk about parametric and non-parametric. And whether we're talking about, explanatory variables or the error terms or whatnot. But this is kind of what flows out of this assumption, trying to be more model free, uh, leads to nonlinear models and non-parametric models, right? Depending on what part we're focused on. Um, and we're not just talking about models with, squared terms, or higher powered terms on our explanatory variables, right? We're not just talking about nonlinear functions. We're talking about mappings between potentially non-Euclidean spaces, right? And so we're not just looking at a one-to-one relationship, as we would be in a function, right? Where both of the space, the x-axis and the y-axis, are the same size, right? They're both infinite single dimension. But rather, we're dealing with mappings where we can be moving from a small space to a larger space. That's called topological lifting, or from a larger space projecting into a smaller space with various forms of dimensionality reduction, like embeddings. Um, and we're trying to again, not make assumptions. And we use this in different ways. But things like neural networks are powerful because they aren't based or derived from these assumptions. They're capable of representing all different kinds of mathematical relationships. Um, so, uh, you know, part of this too, part of what has driven this, part of the advances in modern data science came out of um, genomics and the Human Genome Project, and also the desire to analyze and understand like three-dimensional brain scans, um, and incredibly large data sets. And this is something, of course, that we have seen in transportation as well, where you know in addition to our traditional data sets like surveys, we now have big data from cell phones and connected vehicles and so forth, um, and that provide us much larger but very different kinds of data on travel patterns, right? And with this, this has led to, big data has led to big models, models with very large numbers of parameters. And even, extended kind of our thinking about the kind, necessary support, statistical support, and so forth. So, um, we're looking at trying to harness big data and partly doing that with truly big models. However, right, there really is danger in this, right? And this can go wrong in a lot of ways. And so this has to go hand in hand with a focus on validation, on out-of-sample validation. Um, we have to be more serious about using holdout samples. Um, and also, we have to be careful about how we measure things and how we set up what our real goal is in terms of our objective functions for training models and so forth. And part of that involves regularization. Which is kind of adding, often there are different ways to do that, partly by modifying our objective functions, partly by using alternative loss functions for our models. And again, we'll talk more about all these things going forward. Um, but lastly, one of the really powerful things, powerful insights I think that we've had that can in some sense falls under this whole bigger models. Um, uh, or sometimes are better, although we do still value the parsimony and so forth. But the fundamental insight here, I think, is a really simple and powerful one, and it's building off the famous George Box quote that all models are wrong, but some are useful. The insight here is that all models are wrong, but different models are wrong in different ways, and so we can use them together to kind of check each other. And we can use, the strengths of one to compensate for the weaknesses of another, and so forth. And so, of course, there are lots of different ways. There are different ways that we can combine multiple models. We can combine them in parallel or in series, and so thus, we have things like bagging and boosting, in particular are related to those two, serial and parallel configurations. Um, but we'll see examples of all of these things going forward. So, and what we hope our aim in all of this, the webinars, the playbook, and everything is that we can leverage some of these insights of modern data science, ensemble modeling, multiple models, nonlinear, non-parametric methods, and models. But we want to try to do it without losing the rich patrimony that we have from classical statistics and econometrics and the behavioral theories of random utility maximization and so forth that we've inherited from those. So we want to strike the right balance, and that's what we hope to do and hope to show you, how you can do as well, by sharing stories, success stories of, examples and places where this is being done, has been done, both some really simple ones and also some more complex ones. So that's my little kind of introduction to the whole, series and whatnot. And with that, I'm going to turn it over here to my colleague, Dr. Rama Balakrishnan, who works with me at Caliper and also teaches at MIT. And he is going to kind of give us a nice introduction to AI and machine learning for TDMs. Rama, take it away.
All right. Thank you, Vince. Should I just share the presentation from my side so I can advance the slides on my own? That
That's fine with me.
okay? Let me try to do that. Can everyone see my screen now? And can you hear me? Okay.
I hear you loud and clear.
All right. Thank you, Vince. All right. So for the rest of this webinar, what I'd like to do is step back a little bit from the overall scope of this project that Vince has basically laid out here, and take a slightly more encompassing, higher level walkthrough through what exactly is artificial intelligence. How does it differ from machine learning? We see these terms a lot these days, and there are some subtle differences between them, and it's good to clarify that. We will look at some broad classifications of machine learning algorithms, how they fall into different categories, and then take a quick view of some applications of machine learning algorithms in travel demand models. Vince has provided a bit of a scope as to what was in this project and so on. I want to take a slightly different tack here and show you that some algorithms that fall within the machine learning umbrella are already very familiar to us, and we've been using them for a long time, right? So we'll take a quick look at that and quickly dive into one specific form of machine learning algorithm, which is the neural network, for various reasons. One is it is perhaps seen as the most powerful algorithm, the most flexible among all the options we have under the machine learning umbrella. It has also driven a lot of buzz and advances in the last 10 years or so in terms of everything we see today under the category of artificial intelligence, AI tools, and so on. They're all built on some form of neural network architecture. So we'll take a little bit of a deep dive through it, hopefully demystify some of the math behind it so that we all can quickly see that the basic concepts are not too difficult to handle. Of course, it scales in very scary fashion, but the basic math behind it is fairly straightforward. And we will make some connections between how you might use a machine learning algorithm in a transportation context. And we'll do this specifically looking at choice modeling, or what is called classification in the machine learning domain. Right? But I think at the end of the day, we should all recognize that this field is evolving very rapidly from almost nothing a few years ago. And we do have a rich heritage of developing econometric models and a certain way of thinking about this, where we look at the data, we try to understand it, we try to put behavior behind it, and so on. So we'll try to juxtapose these two together and have some concluding thoughts as to how we might help these machines learn better with a more human touch to it, where we don't completely lose control of the process, but somehow we guide the machines to help us rather than just take over. Right? So that's the general idea for the remainder of this talk. So up front, I thought we'd get some basic terminology out of the way because for those of us who've spent a lot of years building travel demand models and such with a more traditional view of things, there are some terminologies out there that have similar underpinnings and ideas, but they sound very different. So I just want to get a few of these out of the way. The model, of course, we are all familiar with. It's a mapping that takes some input data, we'll call them X, what we might typically refer to as independent variables, and it transforms them or maps them into some output Y, right? So the Y is the result of transforming that X through the model. We typically denote the model's output as Y hat. because the y is the observation from the field, whereas y hat is an estimate that the model gives us. And in general, when we try to estimate these models, we have a measure that quantifies the deviation or the error between this y and the y hat through some mathematical construct, and we optimize that. We reduce that error to be as low as possible. That gives us a model that fits well. So in the machine learning slash artificial intelligence parlance, that process of estimating models becomes model training, where the data is used to fit what we say is estimate a model is now fitting a model. It's basically identifying the parameters in that model to best reflect the data that we have going into that model structure. Right? So the data set that we use to train or estimate a model, whatever that structure of the model might be, typically tends to be called one of two types, either a labeled data set or an unlabeled data set. Now, a labeled data set is probably what most of us have been very familiar with all these years. You have a certain number of variables, say x1, x2, x3, contained within that variable x. These variables in machine learning parlance are called features. So if you see the term features, variables, they're all basically the same idea. These are the independent variables available to us. And in a labeled data set, in addition to to these x's, we also have the outcome, right? Something was measured that we're trying to model. In the example on the top here, you have a couple of x's. One is household income. The other is the distance from the city center of the residence, let's say, right? So these would be x1 and x2. And the color of the dots actually indicates whether that person commutes to work by bus or by car, right? So in addition to x1 and x2, these two variables on the two axes, you have this third variable y that basically tells you whether the mode of transport that somebody took. So that is a revealed preference. The training data set that we have contains an additional column that tells us what that y is. So this is a labeled data set where you have both x and y. Contrasting to this, you have what are called unlabeled data sets, which are more along the lines of we have some x's that describe the survey records or the data records, but we do not have any particular outcome. So in this example on the right, you again have two x's. One is household income, the other is number of cars, but there is nothing really revealing about what these people are. There is no choice they make. There is no response they give you about a decision they take, right? So an unlabeled data set would be a free-for-all. You could look at this and try to figure out if there are groups of people here that might be looking at a certain transportation problem in different ways. For example, green lifestyle choice, things like that. Something latent which is not really directly revealed in the data, but perhaps something for the modeler or a machine to look at and try to infer. Right. So these are some basic terminologies, and some of these terms might actually show up in the rest of this presentation. So I drew up this graphic to try to differentiate between different terminologies we have floating around in the AI space, right? So there is the term artificial intelligence, of course. There is machine learning. There are other terms like neural networks, deep learning, and so on. So I wanted to spend a few minutes here to try to kind of put this in order. Let's try to see if we can um, arrange this in some fashion, right? So artificial intelligence generally is a very loose term. It basically pertains to the concept of teaching machines to think, learn, and act and make decisions like human beings do. And on the face of it, that doesn't look like something you can quantify very easily and measure, right? And it's probably true, but you cannot. But in general, the consensus is that machine intelligence can be broadly classified into three different types. One is called artificial narrow intelligence, or ANI. And everything we've seen so far, going from everything from machine learning algorithms all the way to large language models and the AI tools that we see in the news every day today and perhaps even use today, are all still in that bracket of artificial narrow intelligence. The two other ones make an assumption that the machines have at least reached the same level of decision making and learning of human beings in general. So artificial general intelligence is where the machines are equal to humans in making those decisions, spotting patterns of the data, learning from them, and trying to navigate around different environments, transferring the knowledge that they learn from one environment to the other, and solving new problems and so on. Artificial superintelligence takes that one step even further, where the machine has now outdone the human race in terms of doing or solving these problems. Right. So these are the three things that the three categories that are generally seen out there, and it's good to know that what we're all seeing today and what we're all trying to advance today is in that first category of A and I. So then what is machine learning? Machine learning is basically a collection of algorithms and tools, technologies that help us try to achieve artificial intelligence of some level. Right? So these are typically methods that require some human handholding. It's not just something it does on its own. Someone has to guide these algorithms. Someone has to decide what type of algorithm to use, given the data type that we have, and someone has to set the parameters in them to get it started. Someone has to monitor it, see if it's doing well, make some decisions about whether some other approach needs to be taken, and so on. But these are the tools, right? So there are still humans in the loop trying to guide the process forward. I'm going to jump a little bit to neural networks and come back to deep learning in a bit. So neural networks, like I mentioned before, are currently the workhorse of everything that's happening in the artificial intelligence space. And one way to look at it is that it is structured after how neurons work in the human brain. Um, and unfortunately, it's not as simple as that. The human brain is an extremely complex organ, and it is currently beyond the scope of science to actually figure out exactly how all of this works. So I think a more rational approach is to think of this as a machine that mimics a simplified brain. It has some components of what the human brain has. It has layers of neurons. Data goes into these layers. The neurons act on them somehow. We'll see in a bit how that actually happens. And then somehow at the right end of the process, predictions emerge. Right? Now, deep learning basically increases the complexity of these neurons. So when we in the next few slides, we will see what a neural network looks like. There are many layers in them. There can be as many layers as you want. And deep learning basically, as the name probably suggests, adds more and more layers into it. So a deep neural network will have a lot more layers than a neural network that is simpler and not deep, right? So deep learning algorithms have a lot of inbuilt capability to extract different combinations or transformations of the input data that you send into it, basically feature extraction, and it has a somewhat automatic way of doing that. It of course comes at the cost of becoming a black box. So it becomes harder as the network becomes deeper and deeper. It becomes harder and harder to actually figure out what these transforms are, and that's of course part of the struggle that we actually grapple with when we try to build models in the domain of transportation. So a little bit about where we stand with all of this, right? How did we get to this point? The term artificial intelligence is not new. It was developed by a professor at Stanford, um, John McCarthy, all the way back in 1955, where he defined artificial intelligence as developing machines that can basically think and learn like human beings. Very general definition. And there has been a lot of research on and off in trying to make some of this operational or something tangible and useful. Um, but it wasn't until the last 10 years or so that this field has actually exploded. And there are several reasons why this has happened. The chart on the left kind of shows you the trajectory and how there was a distinct shift after 2010. There are three components that actually fuel this productivity that we're seeing in the last few years. One, of course, is the assembling of labeled data sets. And most of the machine learning progress has been done based on what are labeled data sets. There were seminal efforts at Stanford, for example, to set up ImageNet, which was trying to just essentially download as many images from the internet as possible and label them with multiple labels, right? And they made it freely available for other researchers to take over and so on. There are so many examples of labeled datasets today, but there weren't too many back then, and a lot of this progress got kickstarted when a couple of individuals decided to create these data sets. Of course, computing power is the other aspect here. These algorithms, neural networks, and so on, in terms of idea, in terms of proof of concept, they've existed for decades, but it's only the power of computing that actually scales them, right? So there's that. But one of the true innovations that has rapidly transformed this whole space in the last decade or so is on the algorithmic side. The idea of transformers that can take loads and loads of data, tokenize them, whether it's text or audio signals or whatever it might be, or images, tokenize them into numbers, and pass them through these large neural networks and so on. So transformer technology, and a seminal paper in 2017 from the researchers at Google with a very catchy title, Attention is All You Need. It's a freely available paper online. It basically catalyzed ChatGPT and everything else that has come since then. So what are the different types of machine learning algorithms? So if you look at it broadly, there are 5 of them. At least there might be more, there might be less, but at least a broad number of these algorithms get classified into these 5 categories. The first one, which we will look at, is supervised machine learning algorithms. These supervised machine learning algorithms are called supervised because they work with labeled data. If you remember what we said a little while ago, labeled data has both the x's as well as the outcomes y. And these data go through the model, and it generates either a continuous forecast or a discrete forecast of some kind. And I've listed some of the common machine learning methods that are classified as supervised learning methods, and you should see that some of these are familiar to you, like regression, both the linear kind and logistic regression, which is essentially binary logic of some kind, right? The other methods that fall under this are decision trees, which you will see a lot of in the second webinar in the series, support vector machines, which are also like a classifier/choice modeling paradigm, and of course, neural networks. The second category here are unsupervised. These methods do not require labeled data. So it's more along the lines of the second example I showed a few slides ago, where you just have the x's. They describe the data, but there is no specific outcome for any one of the data points, and it's up to the method to come up with something, right? So one of the key unsupervised learning methods is k-means clustering, or any of these clustering methods that are out there that take these points and try to logically group them into subsets, right? One could think of this, if you wanted a parallel in our econometric literature, you could think of it as trying to identify latent classes or latent groups in your data set, right? Something that's not necessarily revealed in the data, but it's something that you're identifying up later on through an analysis. Vince also mentioned principal component analysis. That's a way of just looking at the data and reducing the dimensionality of the problem, though it has to be said that with the ramp up of computing powers in recent years, the role of principal component analysis is actually reducing somewhat. Then you have a class, 3 other classes of machine learning algorithms that kind of run away from the supervised and the unsupervised paradigms a little bit. The first one is self-supervised. So these are algorithms that look at data that's not labeled, but somehow has a way of generating labels for them, and then using those labels in a supervised fashion to proceed further. And typically, this works well with a lot of structured data, repetitive data that happens with natural language processing, computer vision, and so on, where the volume of data is so large that some of the other approaches that fall under supervised and unsupervised are not very well equipped to deal with that. The fourth in this category, in these categories, is reinforcement learning. Some of you must have heard of this as well. This is going back to how you would, if you wanted a parallel, how you would train a puppy to behave. You provide incentives when so-called good behavior is exhibited, and you provide penalties or punishments when bad behavior is exhibited. So It is a way of starting with a clean slate and essentially only giving the guidance to the program of what the end goal is. You have a certain goal to achieve it in whatever you want. But as you try to go about achieving that, we're going to give you some feedback about whether you're improving the process or you're not. So reinforcement learning became very popular in the video game development industry, and also in the branch of computer science that tried to figure out if machines could play certain games like Go or chess and things of that kind. Right. So all of that was actually trained using reinforcement learning of some kind. And the last category here is semi-supervised, where you have small labeled data sets, and the machine learns a little bit from that, but then it tries to extrapolate that to much larger unlabeled data sets to try to transfer that information over. One of the most popular approaches here is the generative adversarial network or GAN framework, which I believe will be covered in the third webinar in this series. So that's a very high overview of how these machine learning models actually fall within all of this. It should be mentioned that everything in the last three categories here is highly experimental, highly research oriented, whereas the first two categories here have seen a lot more application in the real world. And hence, there is a lot of empirical and practical knowledge that has been gathered about what works and what does not work in different settings. So a quick word about some of the machine learning algorithms that we might already be familiar with, especially in the transportation domain. Linear regression, of course, is now considered part of machine learning. It's been around for ages, right? And in the travel demand modeling domain, you see it a lot. You see it a lot in trip generation models, especially when you have to estimate attraction variables at the zone level. Linear regression is heavily used or is often the model of choice, right? Logistic regression is the second topic that usually shows up if you take a class in machine learning. It is an extension of linear regression, except that it is a discretized version of it with a special error structure at the end of it. And it essentially boils down to binary logit. Right? Logistic regression is binary logit, and its multinomial extension, we know it as multinomial logit. And we've seen this a lot in our travel demand models, definitely in terms of more choice, but also more increasingly in the context of destination choice. And in the activity-based and hybrid modeling paradigms, various other choices as well, including tour frequencies, activity duration, start time, stop frequencies, destinations, and things of that kind. Now, there are some extensions to these kinds of logit models that are currently at least not under the purview of machine learning, and these are everything we've seen in the nested logit uh, uh, branch of choice modeling, for instance, as well as other more theoretically complicated choice modeling frameworks, including kernel logit, mixed logit, uh, cross-nest logit, and what have you. All of this basically relaxes some of the strict assumptions behind multinomial logit, and they've been around in the theory, but they aren't as popular in practice in travel demand modeling, owing to some of the underlying complexities of implementing them and so on. You see a couple of examples here on the right, tree structures for multinomial logit, nested logit in the mode choice context. I'll also mention decision trees here, mainly because we've already seen some uptake of this machine learning algorithm in travel demand modeling, especially in the trip generation phase. Vince alluded to it, but more on this in the next webinar when there will be a lot more detail about all of this. So let's take a look at where we are in travel demand modeling today, where we typically rely a lot on our well-known, well-established, theoretically driven econometric models, right? There are some very nice properties to these models that we use day in and day out. They have explainable behaviors. The parameters that we get from these model estimations are transparent. We can see them. These are not black boxes. We can check the sensitivities of these coefficients. You can get t-statistics out of the estimations. You can check to see if a variable is significant, if it has the right sign, if the ratios of some of these coefficients make sense, and so on and so forth. And all of this is extremely important because we have to always remember that we're building models to forecast, right? Not necessarily only to explain the base case. And when you want to forecast models into the future, you do want to be sure of what kind of sensitivities and what direction the model is going to take when you make certain changes to the inputs. And that level of transparency is essentially a no-brainer. You do need it in our models. But there are certain limitations that we face day in and day out with these econometric models, right? When we are tasked with estimating these models, we identify the key variables slowly and by trial and error. It's not an automatic process by no means of imagination. We have to look at the data. Every location is different. Every survey data set is different. There might be some overarching commonalities, like a mode choice model having a travel time effect that has a negative coefficient and so on. But in order to make the model fit better and explain the local context better, it's somewhat of a tedious process of exploring the data, trying out different things, seeing what works, what does not work, and so on. Um, and our survey data sets are typically relatively small as well. We all know they're costly to repeat and costly to keep processing again. So they happen sporadically, not as frequently as we would all like. And there are some other issues with some of these econometric models as well. If you take Logit, for instance, it has what is called a symmetric response. So from a given point, if you let's say there is a toll in effect today, the response you get from the model by increasing the toll by a certain amount and decreasing by the same amount is symmetric. So it kind of ignores the fact that some people or a lot of people might actually view an increase very differently than a decrease. So there's work being done to relax some of these assumptions, like Joan Walker and Timothy Brathwaite at UC Berkeley have a recent paper where they relaxed this symmetric assumption and developed a class of multinomial logit models that can capture that asymmetric response. But while there are such enhancements and extensions to the state of the art, it does remain very intractable in practice. So we're all continuing to use the models that are easy to implement or have already been implemented and tested and so on. And that extra flexibility actually comes with a very high cost in terms of moving them into practice. So that brings us to the main part of this section of the webinar, which is neural networks. So in the context of choice modeling, which we have taken here, can we look at a different machine learning approach that can give us a lot more in return? So I want to take a little bit of time here to explain the mathematical mechanics behind neural networks. Not too complicated, I hope, but just enough to give a sense of what exactly happens here. So what is a neural network? A neural network essentially has the input layer. So everything here is a layer. The input layer essentially consists of all the x's that we have, the variables that we have in our data set. And we have an output layer from which you get the prediction of the model, the y hat. So what happens in between is a bunch of hidden layers. A neural network has to have at least one hidden layer. So the simplest one would just have one. If you removed all the hidden layers and just had the input layer and the output layer, you basically collapse back to your econometric way of doing things, right? And we'll talk a little bit about when, under what conditions, a neural network might become a multinomial logit model, for instance. But in general, a neural network, if you call it a neural network, it has at least one hidden layer. The example here has three, right? And each of these layers has nodes in there called neurons. Right? So this is where the terminology from the brain analogy kind of shows up. So you have these neurons that are part of the brain, and each layer here is made of these neurons. Each layer can have a different number of neurons. There is really no rule as to how many neurons should be in any layer. There is neither any rule that tells you how many layers there should be. If you keep stacking layers in there, you get closer and closer to a deep neural network, way more complex, way more ability to predict more accurately, but we'll see in a bit what cost that comes at. So For now, it's useful to just understand that there are layers between the input and the output. Each layer has these neurons. A layer takes some inputs and it produces some output. So each layer takes some input, performs some operations on them, creates some output, and throws it over to the next layer in the chain. And this goes on from left to right. What are those calculations? We'll take a look at them on the right. So I've taken that second hidden layer here as an example, and it has 4 neurons in this case, right? It takes as input whatever comes out of the first layer. So let's call that A1. Note that it has an arrow on top, it's a vector. The size of A1 is basically the number of neurons in the first layer, right? So the first layer had 5 neurons in it. So A1 is a vector of 5 for every data record. Right? So those 5 values go into hidden layer 2, which has 4 neurons. Each neuron here now applies a linear transform on this A1 vector. Right? Each neuron has a weight vector Wj and a bias vector, a bias scalar Bj. So it takes that A1, computes a dot product with Wj. So Wj has the same dimensionality as A1. That gives you a scalar. You add the Bj to it. That's your linear transform. That passes through an activation function, G, and that activation function returns a single value, A2J. Right? So you're going to collect these A2Js, one for every neuron in this hidden layer. So there is an A2 for the first one, an A2 for the second one, third, and fourth. So you get 4 A2s coming out. The A2 vector has 4 values. And those values go into hidden layer 3. Right? So if you look to the left of that green layer, the blue layer is taking the input values X. It's doing the same kind of operations, computing those transforms, computing A1, sending it over to A2. A2 is taking A1, doing similar operations, generating A2, which goes into A3 and so on. And finally, the output layer takes whatever the previous layer gives it, does some similar kind of math on it, and it gives you your output. Right? So this is the basic structure. And this is how neural networks are applied. Assuming that you know all these weights, all these Wjs and all these Bjs, you can take your X's, feed them in, and actually walk your way through these calculations all the way to the right and get your prediction. Right? The difficulty, of course, is knowing what these weights are. Right? That's where the crux of the neural network actually lies. So what are these activation functions, right? Because that seems to be the key to figuring out how these calculations progress from left to right in the neural network. There are some different options of what you might use for this activation function. Remember, the activation function takes a single value, like a linear transform of some other variables, passes it through the activation function, returns a single value on the other side, right? So if you look at one of the most commonly used activation functions in neural networks, the sigmoid function, it has the shape on the right, and those of you who are familiar with choice modeling will immediately recognize this as the logit curve. Right? And if you look at the equation there, 1 over 1 plus e to the minus z, that is exactly the equation you get with binary logit, where minus z is basically the difference in the utilities of the two options that you're trying to choose between. So if you apply the neural network with the sigmoid activation function, you're essentially going to be mimicking a binary logit kind of situation. There is an extension of sigmoid called the softmax activation function, which essentially moves from binary to multinomial choice. One different type of activation function, which might look very counterintuitive to start with, but is apparently heavily used in practice, is what is called ReLU, which stands for rectilinear unit. And it has a linear structure, a piecewise linear structure that is shown on the right here. And it's a simple function. It doesn't have this nonlinear complexity of the sigmoid function. Rather, it just calculates the max of the value relative to 0. So if the value that goes into the function is negative, it returns 0. If it is positive, it returns the value that it got. That's it. So this might feel counterintuitive, but it actually gives the neural network unprecedented flexibility to approximate any function. If you have enough hidden layers and neurons and you apply this piecewise linear function enough times, then any nonlinear function can be approximated to any arbitrary level of accuracy by enough of these functions. Right? And the reason why ReLU has been generated or tried and tested is because the sigmoid function in softmax have something called the vanishing gradient problem, which we won't get into here, but it basically gets stuck in some local optima where it's unable to get out of that location and try to find better solutions. So it turns out there is a whole bunch of practical guidance on these different activation functions, what works, what does not work, and so on. So this is all well and good. We've discussed what a neural network is. We've discussed how it operates, how it takes the data on the left-hand side and transforms it into something actionable or classifiable on the right-hand side. What we haven't yet talked about is where these weights and biases come from, right? So to apply the model, you need these weights and biases. So what we've described in the previous couple of slides is what is called forward propagation. If you know all the weights, you send the x's in, you apply the weights and the transforms, and you get your answer. And there is a reverse process called backward propagation, which is an optimization step that actually helps you train this neural network and identify these WJs and BJs. Right? So in backward propagation, you can assume that what happens is you go through a first pass, you assume some weights to start with, you apply the forward pass, you get your y hats on the right side, you compare them with the y's that were in your labeled data set, right? So this automatically means neural networks are supervised and therefore they need a labeled data set. You cannot apply these on unlabeled data sets. So for every record I in your data set, in your training data set, if you have a yi